Hello student, welcome you to my YouTube channel. In this video I will continue with the topic solution. This is my second video. Please go through the first video and then continue with the second video. And in this video I am going to tell you what is meant by vapor pressure, what is meant by Raoult's law for solution of liquid in liquid, and then we'll move on to ideal solution, non-ideal solution, and what is meant by azeotropic mixture. So to know all these things, stay with me till the end of this video, and if you get benefited from my video, please don't forget to like my video, share my video, and please do subscribe my channel. So let's start with our topic. Before starting, I would like to advise you to keep pen and a notebook with you so that you can note down the important points during the discussion. Okay, let's start with the first term, vapor pressure. This is a very simple term, vapor pressure. Consider you have a liquid in a closed container. In a closed container. Now we all know evaporation takes place from the surface and vapor will form, and this vapor will condense back again to form liquid. Okay, so there is an equilibrium between the vapor and the liquid. This we have learned in class 11 topic. So when vapor is formed, the vapor will exert some pressure on the liquid, and that pressure is called vapor pressure. So write down the definition of vapor pressure. The pressure exerted by the vapor above the liquid surface in equilibrium with the liquid is called vapor pressure. The pressure exerted by the vapor above the liquid surface in equilibrium with the liquid at a given temperature is called vapor pressure. Now you have to mention the temperature, because suppose you have two different temperatures. You have water at say 20 degrees Celsius. In another container you have same water at say 40 degrees Celsius. Now in case of the first one, 20 degree, the evaporation rate will be less, and so amount of vapor will be less. In case of 40 degree, evaporation rate will be high and the amount of vapor formation will be high. So in case of 40 degree, the vapor pressure will be greater than the vapor pressure in case of 20 degree. Okay. Now this vapor pressure also depends on another factor, that is called intermolecular forces of attraction. Suppose you have two liquids. One is water, another you have acetone. Now, in case of water, the intermolecular forces of attraction is hydrogen bonding. In case of acetone, the intermolecular forces of attraction is dipole-dipole. And we know dipole-dipole interaction is weaker than hydrogen bonding. So in case of acetone, the tendency to escape into the vapor phase will be higher, and so the vapor pressure will be higher. So we can write P1, if it is P2, then P2 is greater than P1. Next we will move on to Raoult's law, that is solution of liquid in liquid. Now I will discuss Raoult's law for liquid in liquid, that is solution of liquid in liquid. Suppose you have one liquid, that is liquid A. You have the second liquid, liquid B. Mix the two liquid and you will get the solution which contain both A and B. Now according to Raoult's law, write down the statement of Raoult's law. At a given temperature, for a solution of two volatile liquid, the partial vapor pressure of each component is directly proportional to the mole fraction of the component in the solution. So in the solution, suppose liquid A is there, B is there, so A will evaporate and A will have a partial pressure of PA, and B will evaporate, it will have a partial pressure of PB. Now in the pure liquid, B will evaporate and its partial pressure will be PB. Here we don't have partial pressure since only component B is present. Again, when component A is present, then this is the pressure of the pure liquid A. So we write PA naught, PB naught. So according to Raoult's law, the partial pressure of each component is directly proportional to mole fraction of the component XA. The partial pressure of B is directly proportional to the mole fraction of the component XB, and so we have PA is equal to PA naught into XA, PB is equal to PB naught into XB. Now this mathematical expression is called the Raoult's law for two volatile liquid. Now if you combine the Dalton's law, it says the total pressure is the sum of the partial pressure PA plus PB. So we can write P total is equal to PA naught XA plus PB naught XB. So this is all about Raoult's law. Now we will move on to P total is equal to PA naught XA plus PB naught XB. Now we will move on to the next topic, that is ideal solution. So write down the statement of ideal solution. Those solutions which obey Raoult's law over entire range of concentration are called ideal solution. Those solutions which obey Raoult's law over entire range of concentration are called ideal solution. So the solution which obey PA is equal to PA naught XA and PB is equal to PB naught XB are called Raoult ideal solution. And in this solution, the P total, as we have already seen, is equal to PA naught XA plus PB naught XB. Now the graphical representation of ideal solution. Graphical representation. You have two equations. PA is equal to PA naught XA, PB is equal to PB naught XB. These two equations are in the form y equal to mx, so it will be a straight line. Another equation you have P total is equal to PA naught XA plus PB naught XB. Now if you convert this entire equation in terms of variable XB only, then you will get P total is equal to PA naught plus PB naught minus PA naught XB. This we can use from XA plus XB equal to 1. Now we plot vapor pressure on the y-axis and mole fraction in the x-axis. When XA is equal to 0, XA the maximum value equal to 1. When XA is 0, then XB is equal to 1, and when XA is 1, XB equal to 0. So put XA equal to 0 in this equation, you will get a point here. And when x equal to 1, you will get a point on this line, say this point, and this point is equal to PA naught. You will get another point like this. This point PB naught, and if you combine both the lines, you will get this P total is equal to PA plus PB, or we can write PA naught XA plus PB naught XB. This line is PA equal to PA naught XA This line is PB is equal to PB naught XB. Okay. Now how you are getting this line? Just simply put XA equal to 0, XB equal to 1, XB equal to 0. In this equation, you will get 2 points and connect the 2 points, you will get the straight line. Okay. Next, we will move on to the molecular level interaction in case of ideal solution. Molecular level interaction. So what is molecular level interaction in case of ideal solution? In case of ideal solution, the A-B interaction is equal to AA interaction or BB interaction. AB interaction is equal to AA interaction and BB interaction. And when AB interaction is equal to AA and BB, in that case, for the solution, delta H0 solution will be 0 and delta V0 solution, del V solution will also be 0. Since the interaction is same, that means the attraction energy, intermolecular forces of attraction is same. So neither heat is released or absorbed during the solution formation. And since attraction is same, the intermolecular distance will be same, and so the volume change will be 0. Now, why the intermolecular interaction between A and B will be same as that of AA and BB? And it will be same in case of certain examples only, not for all cases. Now, if you consider benzene and toluene, both of them has similar structure, both are non-polar, so the forces of attraction between both the molecule are London force, and hence the if this component is A and this component is the B component, then AB interaction is also London force, AA interaction is also London force, BB interaction is also London force. So they will form ideal solution. Another example. Chlorobenzene, bromobenzene will form ideal solution. Another example, 1, 2, 3, 4, 5, 6, hexane. 1, 2, 3, 4, 5, 6, 7. So this is N-hexane, this is N-heptane. So both will form ideal solution. So whenever the molecular shape and size are similar, they will have similar type of attraction and hence they can form ideal solution. Next we will move on to the non-ideal solution. Now non-ideal solution. Now those solutions which does not obey Raoult's law over entire range of concentration are called non-ideal solution. Now for such solution, the vapor pressure of the solution is either greater than or less than what expected from Raoult's law. So, for such solution, the vapor pressure will be either greater than or less than what expected from Raoult's law. If the vapor pressure is greater than expected from Raoult's law, we call it positive deviation. And if the vapor pressure is lower than what expected from Raoult's law, we call it negative deviation. Now, in case of positive deviation, P total is greater than PA naught XA plus PB naught XB. Here, P total is less than PA naught XA plus PB naught XB. For ideal solution, it is equal to. It is equal to. For non-ideal solution, if it is greater, we call it positive. If it is less, we call it negative. So again, we will have PA will be greater than PA not XA and PB will be greater than PB not XB. Here also, PA is less than PA not XA and PB is less than PB not XB. Okay. Now the second factor, delta H solution. For such solution, delta H solution will be greater than 0. Delta V solution, that will be greater than 0. For this one, delta H solution less than 0. Delta V solution less than 0. Third, the interaction. In this case, the AB interaction is less than AA or BB interaction. Here, AB interaction is more than AA or BB interaction. Now we'll see the molecular level interaction, and next we'll move to the graphical presentation of positive and negative deviation. So for positive deviation, this is vapor pressure axis, this is mole fraction axis, XA equal to 0, XA equal to 1, XB equal to 1, XB equal to 0. So we have the ideal solution equation like this. The dotted line. Now for positive deviation, the vapor pressure of the solution will be greater than that expected from Raoult's law. This is PB naught, this is PA naught. Now in case of negative deviation, XA equal to 0, XA equal to 1, XB equal to 1, XB equal to 0. So again we have the ideal case, and for negative deviation, the vapor pressure will be less than that expected from Raoult's law. This is PA naught. This is PB naught, and this is the vapor pressure axis. So you can see in positive deviation the vapor pressure is greater. In case of negative deviation, the vapor pressure is less than that expected from Raoult's law. The dotted line is for the ideal case, and the actual line is the non-ideal case, either positive or negative deviation. Now, example of such positive and negative deviation. Positive deviation, example, say acetone plus carbon tetrachloride. Second, ethanol plus water. For non-ideal solution, chloroform plus acetone. Second, say HCl plus water. So all this show non-ideal behavior, this show non-ideal behavior. Here it is positive deviation, here it is negative deviation. Okay. Next, we will move on to azeotropic mixture. What is meant by azeotropes or azeotropic mixture? So write down the statement of azeotropic mixture, the definition. Write down. Liquid mixture which boil at constant temperature and can distill without change in composition are called azeotropes or azeotropic mixture. Once again, liquid mixture which boils at constant temperature and can be distilled without change in composition are called azeotropic mixture. Now there are two types of azeotropic mixture. One is called maximum boiling azeotropic mixture, another is called minimum boiling azeotropic mixture. So the first one is maximum boiling azeotropic mixture, another is minimum boiling. Now, maximum boiling and minimum boiling, what does it mean? Now, what is meant by boiling point? Now, the definition for boiling point is, it is the temperature at which the vapor pressure reaches atmospheric pressure. The vapor pressure of the solution reaches atmospheric pressure. So, in case of positive deviation, where you have seen that the vapor pressure of the solution is greater than the ideal solution. Vapor pressure is greater. So whenever the vapor pressure is greater, then the tendency to reach the atmospheric pressure will be higher. So those solutions will boil at a lower boiling point and hence are called minimum boiling azeotrope. For example, minimum boiling azeotrope are shown by solution with large positive deviation minimum boiling azeotrope are shown by solution with large positive deviation. For example, ethanol water, the ratio it is 95.5% and 4.5% is water. Maximum boiling azeotrope, in case of negative deviation, you have seen the vapor pressure is less than the ideal vapor pressure. That means to reach atmospheric pressure, you need more heat. So the solution will boil at a higher temperature. So we say maximum boiling azeotrope. So solution with large negative deviation shows maximum boiling azeotrope. Example, HCl water, the exact ratio is 20:80. Nitric acid water, the exact ratio is 68:32. So hope you like this video, and if you get benefited, please do share this video with your friend and like my video, subscribe my channel. Thank you.